листа.
Еще надо вверх.
Идем.
Может проверить.
Да.
Не, ну там не показывается.
Ну, может быть, сюда.
Можно включить еще.
Ага, ты говоришь? Вот да, все что-то не.
Идем. А тут кольцо.
В общем, она идет, но только вот эта доска.
И что?
Когда доска
А вот если мы на второй сделаем такую же доску? Вот нажимать X, что ли?
А вы можете это, наверное, проматывать вот это.
Это можно проматывать. Или что ты хочешь
Вот
сказать?
это проматывать можно вниз.
И это может проматывать вниз, да? А вот это может проматывать
А
вниз?
это нет.
Это нельзя проматывать вниз?
Кажется, нет.
Как? Нельзя?
Ну вот тут вы можете вот так делать.
Нет.
И у вас страница не спускается.
Ну, это хорошо, да, но все-таки...
Нет, это тоже может проматывать вниз. Это тоже может проматывать вниз.
Да.
Если вот на стрелочку нажать. Нет, нужно убрать. Да.
Ну ладно, вот одна доска. Ну как бы, ну вы...
А тут никак не удается.
Нет, не выходит. Вы пишите на
Сейчас,
звук,
может быть, тут можно?
но сказали, только одна.
Нельзя двигаться?
Я не вижу. Ну вот так можно.
И тут расширенный экран.
Да, что вы видите? Вот общий вид. Вот здесь можно быть.
Хорошо.
Так, общий вид можно.
Сейчас там съешь, но ты не что 10. Так что
Ну, здесь пошел. Вот еще одна.
Нажать. Вверх, правильно.
а вот я хочу, чтобы это закончить.
Даже не может.
Да, вот.
Да, сам же там.
Да, почему?
Там начинается уже.
Я, кстати... это, наверное, не очень хорошо, да?
Нет, если ты раздвинешь, то...
Сейчас, нет, мы включили, мне кажется, мы включили, короче, Android. Сейчас только что на твоей доске, нет?
А как это различается?
Вот, теперь все должно быть хорошо.
Сейчас. Да, полетел.
Все, можно что-то делать.
Okay, sorry for these complications. So last time we studied the representation of SP2, SL2, and produced some discrete series representations of SL2 of dimension q minus 1 over 2. Now we are going to construct all the discrete series representations. But to this end, we will need to use the representation of SP4. So, well, okay. So we start with the symplectic vector space. Two-dimensional. And now, because we will have to use FQ and FQ square, maybe let me just write F to make annotations shorter. And F hat will be F cube squared. So the quadratic extension. So it is as a vector space over FQ, it is two-dimensional, but some other. It's not V. We will view it rather as a vector space with a symmetric form. Quadratic. Just norm of x is x bar is x to the power q plus 1. But maybe I want to multiply everything by 2, since anyway we're not interested in 2. Because I want the corresponding bilinear form to well, not have denominators. So polarization n of x y is just what do I call it, q of x. So it will be 1/2 q of x plus y minus q of x minus q of y, linear polarization, and it will be equal to x y bar plus x bar y. Okay, and now I consider the tensor product of those two. V tensor f hat. So now this has a symplectic form, skew symmetric, this has symmetric form, and so the tensor product is again symplectic. Namely, the pairing of V1 tensor x1 and V2 tensor x2 will be equal to the pairing of V1 V2 times x1 x2 bar plus x1 bar x2. Just the tensor product of those two forms. Okay. And now we have the symplectic group of V, and we also have the orthogonal group of F hat, and certainly their product embeds into the symplectic group of W. So we get those symplectic morphisms of this four-dimensional space, which are compatible with its tensor product decomposition. Okay, this is called in general dual reductive pair. Well, because both groups are reductive, and well, they commute, but moreover, everything which commutes with symplectic group is this, and everything which commutes with the orthogonal group is symplectic. So they are commutants of each other, so to say. Okay, but it's true, but we don't even need it. We only need that this product embeds into the symplectic group, and now inside of this orthogonal group, we will need something like a special orthogonal group, namely these are the elements in this quadratic extension of norm 1. Okay, so it's like a circle. S1, which is equal to SO2 over complex numbers. Okay. Now we consider the representation of SP of W and restrict it to this product, SPV times F hat 1. Okay, and now let's make it as explicit as possible. So choose a Lagrangian line L in V. So V was two-dimensional, and Lagrangian subspace is one-dimensional, so it's just one line. Then if we take the tensor product L tensor F hat, this will be lambda Lagrangian in W, two-dimensional Lagrangian subspace. Okay, and now this V representation, say A, capital A, is from the symplectic group of W into automorphisms of functions on this Lagrangian space. Okay, so last time we discussed that it is representation of some metaplectic central extension, but then it reduces to, the extension is trivial, and over a finite field you can split it, and so we obtain the representation of a symplectic group. Okay, and well, in fact, maybe we, last time we also considered the odd and even functions, so such decomposition also works here. So we can decompose, say, the odd functions according to the characters of our circle. Okay, and namely, we get not all the characters, but because of this odd condition, we'll have all the characters eta, such that eta of -1 is -1. Yeah, because of this odd condition. Okay, so we consider this space of odd functions, well, eta invariant. So this is the space of functions f from this field because we take our line and we multiply it by two-dimensional space, this field, and we can trivialize this line and identify this tensor product with the field itself, the two-dimensional vector space. But then because of the odd condition, the value at 0 is 0, so we view it as functions on the punctured field, yeah, vanishing at the origin. And the functions such that f of ax is eta of a, f of x, well, for any a in the circle and x in the punctured plane, the field. Okay. Now, I forgot what do I do here? Yes, but how?
Ладошка желтая вверху.
Like this.
Да.
And no other. Okay. Okay. So now what do we see that number of such characters eta is what? How many characters do we get? So first of all, how many elements we have in here? There's some abelian group, this circle, how many elements it has? These are elements in the quadratic extension of norm 1. How many elements in the quadratic extension do we have? Q squared, right. And how many of them have norm 1?
Q.
Something like this, yes. So non-zero elements, invertible elements, we have a q squared minus 1. Then we have a homomorphism from the norm homomorphism from this group of order q squared minus 1 to the multiplicative group of the ground field, q minus 1. So what's the kernel? Yes, q plus 1. Very good. Thank you very much.
And the characters eta, we have to take half of them.
Right, right. So we get the number of eta is q plus 1 over, because of this condition that eta of negative 1 is negative 1. In principle, it would be also for, I mean, if you square any such character, the value will be 1. So it's just exactly 1 half. Very good. And now, what is the dimension of this eigenspace? Well, maybe you remember. Oh, sorry. Oops. Yeah. Everything vanished or what?
Нет, вверх.
No?
Вверх.
I don't.
Возьмите, вот там есть ладошка вот сверху.
Да, да.
Ловушка сверху.
Ладошка.
Ладошка.
Да, желтая такая.
Желтая ладошка. Вот.
Ага, вот вы ей, короче, вот да, вот ей ставите, да.
No?
Да, все хорошо.
Все, вверх.
Чуть аккуратно.
Okay, now I'm
Приблизьтесь теперь
Ага.
зума.
Правый нижний угол.
Мгм.
И вверх.
И опять вверх.
О, бадзу.
Ну, сейчас.
No, I'm lost.
Oh.
Oh, good. But zoom is like no, like this. Okay.
Все, теперь убейте эту, нажмите на писать. Нет, там карандашки слева.
Here.
Слева карандашик, да. Все.
Thanks. So, what is the dimension of the space of odd functions, which was thoroughly studied last time?
Q minus 1.
Right. So this was for one-dimensional case, and now it's two-dimensional
Ah.
case.
М,
Yes.
Q squared minus 1 over 2.
Right. Thank you. Very good. So we have that many characters, and we decompose this space into such eigen subspaces. So the dimension of each one is what?
Q minus 1.
Yes. Thank you.
минус 1.
Okay. And also if q equals 4k plus 1, then there is a character eta mod such that eta mod squared is 1, and then the corresponding eigenspace will split into a direct sum of 2. I don't know how to say it. I don't know any. Well, let me. Is a direct sum of 2 q minus 1 over 2-dimensional subspaces we studied last time. But otherwise, they're all irreducible of this dimension. And what else can we say? Maybe we can also say that if we change the eigen character to the opposite one, the representation is isomorphic. For example, through the same Radon transform we studied last time, or Fourier transform, or whatever. So. It's isomorphic to the opposite. And also we can study the even part. Decomposes according to characters, say xi, such that xi of -1 is now +1. Okay, and there are again as many of them. The number of such xi is also +1 over 2. And now what is the dimension of the corresponding eigenspaces? So here is what? Yes, q squared plus 1 over 2. And what about the eigenspaces?
Cool. This one, no.
There is some slight problem that q squared plus 1 is not divisible by q plus 1. Why? What shall we do? What happens? Well, there is one, yes?
I think we should look at values at 0 maybe. Well, I have an unrelated question.
Yes.
There was a remark. If q is for k plus 1, there is a character at a 0. At a 0 which is satisfies the condition that the value is -1 is -1. But I think it exists only if q is 3 modulo 4, not 1 modulo 4. Is it?
Let's see. So this this group has dimension q plus 1, and maybe you're right. So if it's -1 modulo 4.
Sorry. Yes, it's correct because I have mistaken the circle group for the Boyle group.
Okay. So as Mikhail says correctly, certainly with respect to all such characters, the eigenspaces again consist of functions vanishing at the origin, except for the case when the character is trivial. Then we have the delta function at the origin is good. Okay, so the dimensions are somewhat different. So if psi is 1, then the space of invariant functions, even and invariant, has dimension which so lambda is two-dimensional over our ground field, so it has q squared elements, and now with respect to the dilations, they are just constant. Psi is just 1. So how many orbits of dilations we have? There is this trivial orbit at the origin of 1 point, and some non-trivial orbits. So how many orbits we have? Well, again, this group consists of q plus 1 elements. It acts on the space of on the set of q squared minus 1 elements. Yeah, the punctured plane, q squared minus 1 elements. So any orbit is of which size?
Q?
Q minus 1. Q minus 1. It's q squared minus 1 divided by q plus 1. So it's q minus 1. But for psi equals 1, there is one extra delta function at the origin. So this is q. And this representation is this type. But but all the rest of the representations have which dimension? We'll just discuss that. In fact. Q minus 1, yeah. The number of orbits. Right. Fine. And again, as before, the representations for xi and xi inverse are isomorphic. And so how many do we get? Well, there were Q plus 1 over 2 altogether, but we removed the trivial one, so it's Q minus 1 over 2. Okay, fine. So we obtained the Q minus 1 over 2 here, and also Q minus 1 over 2 there. Sorry, the number of such atoms was Q plus 1 over 2, and
I think
yes.
We said in the end that C lambda xi is isomorphic to C lambda xi inverse, but previously we don't we consider them without this isomorphism. That's why we have Q minus 1 but not Q minus 1 half. No?
Okay, so the total number was Q plus 1 over 2.
Yeah.
And then, okay, the total number here will also be Q minus 1 over 2, but there will be such an isomorphism. Fine, so what do I do here? I also...
Вот там вот курсорчик, нажмите на курсорчик и пролистайте вниз.
Press here and then does this?
Да, yes.
Okay.
Теперь на ручку.
Sorry. Thanks. Okay, so now I want to write down explicit formulas. For the action of SP2 or SL2 in these representations. Well, we discussed representations of GL2, and now we are constructing representations of SL2, but in the process of writing down explicit formulas, we will see that those representations of SL2 can be naturally extended to the whole of GL2. Okay, and they will be Q minus 1 dimensional, and so they will be cuspidal. Okay, so what we have constructed are the restrictions of cuspidal representations of GL2 to SL2. And now we want to extend just by the action of center of GL2 to the whole of GL2. First of all, we know that they all act in the functions in lambda. That was just the quadratic extension. the first observation is that, well, maybe key observation. Is that when we embed SP of V into SP of W, then we just tensor by some two-dimensional space. Yeah, how was it? W was V tensor f hat, and the embedding of this smaller symplectic group in this bigger symplectic group is just sort of doubling. So alpha, beta, gamma, delta, well, in appropriate coordinates, goes to alpha, alpha, beta, beta, gamma, gamma, delta, delta. Oops. So we just tensor with two-dimensional vector space, and so each element of the symplectic 2x2 matrix becomes a symplectic 4x4 matrix just by doubling, and this means that the restriction of the cocycle C, well, coming from SP, well, maybe not SP, I should say, metaplectic extension of W. There's now this cocycle 2 SPV embedded into SPW is well, so it's doubled, and hence the C restricted to SP of V is 0, because anyway we computed that this cocycle C was of order 2. Yeah, we had to represent it as a well, we proved that the square of this cocycle was a coboundary of something, right? This was our key computation. But now, because of this doubling, when restricted to this subgroup, it is trivial anyway. Yeah? And in fact, it is very important in over bigger fields, say over p-adic fields or real fields, then you will always have, let's say, QP or say real ground field. We also have an embedding of SPV times O of F hat into SP of W. And now there is this metaplectic extension of the group which does not split anymore. Yes, so when we discussed our representation, I used that over finite fields, it's really a representation of symplectic group, not of metaplectic cover. But over local fields, it is not a representation of symplectic group. It is really a representation of metaplectic cover. But this embedding extends, can be lifted to here. So the metaplectic extension restricted to this product splits. Okay? Over finite field, there's nothing to it because it splits everywhere at all. But over local fields, it will split all over such products, not over the whole symplectic group SPW. Okay, so that's how it is proved. Okay. Okay, so now I press here. Go up. I press here. I continue. Okay, so well, the conclusion is that the explicit formulas for a G when G is in SPV hold true on the nose and not just up to plus minus 1. Okay, so we wrote down some explicit formulas that they were true up to a constant. Then we argued this constant was just plus minus 1. And over finite field we're able to somehow, by multiplying by some determinant, make the determinant exactly 1 as opposed to plus minus 1 to find some formulas for representation. But when we restrict to such matrices, all the determinants in question are just 1. And so those formulas, which were written in your home assignment, for example, the explicit formulas for specific matrices, are just absolutely true. They don't need any corrections by signs. So, for example, if we want to find something which looks like Fourier transform, then it is really a Fourier transform. So this lambda is an element in our Lagrangian space, which is the quadratic extension. And this value is just the Fourier transform of the function f evaluated at lambda. Well, if somebody remembers the exact formulas, there was minus sign there, but this was for another matrix, which is 1 here, negative 1 apparent. So this matches our standard conventions, and the Fourier transform is defined just by the standard formula. You multiply by the additive character of some pairing, and this pairing is the one we have in the very beginning, lambda mu bar plus lambda bar. Okay? Just the bilinear form, pairing two elements of. So you usually should go to the dual space, but our space is self-dual because of our choice of this bilinear symmetric form. Well, by this pair. Okay, in the beginning, this pair. Fine. Now we choose a character eta tilde. So eta was defined on this unit circle, right? And now extended to the whole multiplicative group, such that the restriction of eta to the unit circle is 8. Okay. and I think that eta is not trivial. Okay. And well, we have an exact sequence. This unit circle is embedded into the whole multiplicative group. And what do you get in the quotient? Yes. Yes, the ground field multiplicative group. What is this? Morphism?
The norm?
Yes, just the norm. Norm of x is x bar is x to the power q plus 1. Okay. And now we can identify the eigenspace of character eta with just the functions on the multiplicative. Sorry. Multiplicative group of the ground field. Just using a section S from here so we know how our functions behave with respect to multiplication by the unit circle. At the origin, anyway, they vanish because this character is non-trivial. Yeah, character is assumed to be non-trivial. So at the origin, our eigenfunctions vanish anyway, and then I just have to specify the value of such function at just one point at any orbit. And well, if you produce some section, not just as a group homomorphism, just any section at all, then you can identify such space with such functions. Okay, just take the value of such eigenfunction on this section. Okay, and then we can rewrite the Fourier transform from functions with eigencharacter eta to the functions with eigencharacter eta inverse via this identification. So I just take this formula and rewrite it. And I get 1 over q, the sum over all invertible elements in the ground field, then the sum over all elements with norm equal to this x, and then psi of lambda mu bar plus lambda bar mu f of lambda. Okay, and then let's just change the variables. Let's write t equals lambda mu bar. And we get 1 over q, the sum over all invertible elements, the sum over norm of t equals x norm of mu, psi of t plus t bar, f of t mu bar inverse. Okay, and now let's sorry.
Yes, one thing.
Okay, so now let's note that that f of t mu bar inverse equals f of sx. So S is our section. That's how we identify eta eigenfunctions on the quadratic extension with functions on the ground field times eta over t mu bar inverse sx inverse, and this is f of sx eta tilde of t eta tilde inverse over sx eta tilde over mu bar inverse, and this is equal to f of sx eta tilde of t eta tilde inverse over x eta tilde over s x bar eta tilde over mu bar inverse. Okay, and we're almost done. So let now mu lie in the section we used, and say mu equals sy for some y. And set g of u is 1 over q, the sum over norm of t equals u, psi of t plus t bar, eta tilde of t. Okay. Then finally we can arrive at the bottom line. Then we have that eta tilde of sy bar, Fourier transform f of sy equals the sum over all invertible elements, eta tilde inverse of x, g of yx, f of sx, eta tilde over sx bar. Okay? And this is what we wanted. So now let me write it down more pictorially. So we define an isomorphism kappa from the eigenfunctions, eta eigenfunctions, to the functions on the invertible, sorry, oops. Elements. Namely, by this section I already used, kappa f of x is f of the section of x, eta tilde of sx bar, and we also define, say, rho from functions on invertible elements to itself, namely rho f of y is the sum over all invertible elements, eta tilde inverse of x, j of yx, f of x. Then the action of kappa identification via kappa intertwines the Fourier transform here and the action of this operator rho there. So we for any character, we identified the eta eigenspace on the quadratic extension with the functions on the ground field, just by using this section from the ground field to the section of norm from the ground field to the quadratic extension. And the Fourier transform acts here, so it must be expressible in some way on functions on the ground field, and it is expressible this way. Okay, and it depends on the choice of lifting of our eigencharacter to the character of the whole multiplicative group of the square quadratic extension. Okay. So this will be the model for our representation, and maybe you remember this from some earlier days. The functions on the multiplicative group of the ground field. It was a model for something else. Late January. So certainly it wasn't your home assignment. well, which groups did we study? So now we're studying GL2, SL2, but before we studied something more elementary. We started with what? Well, in the process, we studied also the Heisenberg group and its von Neumann representation. But before that, what did we do? Before that, we studied the induced representations from Borel, the principal series, but in the process, we studied something. For Jacquet functor, well, there was this mirabolic group P. AB01. And it had certainly many characters, but also just one higher dimensional representation. That was exactly this.
This functions with some zero.
Right, but then in your home assignment, using Fourier transform, you had to identify it with the functions on F star. Well, in fact, you just, how do you construct this representation? You construct this representation, there is this unipotent subgroup, strictly upper triangular. You take its character psi, and you induce. But when you induce, you essentially get, well, twisted functions on the quotient group. But the quotient group is just this, the multiplicative group of the field. So this representation identifies with functions on the field. And well, there are some explicit formulas for this. Okay? So this P acts here. And remember that how we argued with this Jacquet functor that, well, there are characters of GL2, one-dimensional, and they're sort of degenerate and not interesting. But any other higher dimensional representation can be of dimension only Q plus 1 if it's induced from Borel, or Q if it's sort of Steinberg, also somewhat induced, almost induced, or Q minus 1 if it is discrete series or cuspidal. Okay? And this means that when you restrict to P, you obtain just this representation for cuspidals, or this representation plus one-dimensional for Steinberg, or this representation plus two-dimensional for induced. Anyway, you get this plus Jacquet functor. Any representation of GL2 when restricted to P is just the direct sum of this and the Jacquet functor. The Jacquet functor can be 0, 1, or two-dimensional. But somehow the most interesting essential part is this, and for cuspidal representation there is nothing else, just this. So the bottom line is that when we restrict our representation to the mirabolic subgroup, you don't somehow see what you started from. They all look the same. After restriction to P, they're all the same. So all the cuspidal are just the same. They're just this representation, irreducible. Okay? But now we have to somehow recall what we started from. So in order to extend it to GL2, you need, in fact, well, you need some central character, which is missing here. And this will add momentarily. But also, you need just this element W, which is 0, what was it, 1, I forgot. 1, negative 1, 0. Okay? If you know this, it generates the whole group. You know restriction to P, you know the central character, and you know the action of that. And in principle, any element of GL2 is the product of some elements of this, here, and the central. Okay? And there we are, because we know the action of P, and the action of this element goes to Fourier transform, and Fourier transform is written down here. So in a sense, this is the description of all the cuspidal representations. Okay? And now let me really do this extension to central character and to the representation of GL2, because so far we really worked with SL2. So I move up.
You need to add a new page.
Huh?
You need to add a new page.
I need to add a new page.
Yes, left bottom.
Good. And how do I do this?
Вон там у вас страничка с ключиком, наверное, на то. Это то.
Страничка с плюсиком. Here.
Ага.
Good. Thank you. Okay, let's do it. This will work. Now I press over here. Okay. So other G, well, they are easy, namely A1 beta 0 1 F of lambda is psi of beta norm of lambda, F of lambda, and what else? Sorry. What else do I want? Well, I want to transform everything. Well, this is a formula for lambda in the two plane in our quadratic extension. But I want to write everything down in terms of functions on f star. Okay, so for this I conclude that kappa A1 beta 0 1 kappa inverse f of x equals psi of beta x f of x. And this is good because this is how our parabolic group really acted on this representation. Well, if you go over your home assignment once again and recall how it acts, it is this really by this formula. Okay, now what else? A alpha 0 0 alpha inverse f of lambda is f of lambda alpha, and hence when I conjugate with by this kappa, I get eta tilde inverse of alpha f of alpha squared x, which is also good because now it can be extended to GL2. See, for SL2 we have alpha inverse, but in GL2 we could have just alpha 1. But because this alpha squared, I can easily extend. So this extends to the Borel subgroup B inside GL2. Namely, I say that A alpha beta 0 delta f of x is equal to eta tilde of delta psi of beta delta inverse x f of alpha delta inverse x. Okay, and the restriction from Borel to this parabolic subgroup. So when delta is 1, is just pi. Well, functions on ground field. Okay, so that's what I just announced. That the restriction to parabolic group will be always the same, but it extends from this parabolic subgroup to the whole Borel of GL2. Okay, well, I have to move away this. Sorry. Now we can extend A to the whole of GL2. So we set A alpha 0, 0, 1, F of lambda is eta tilde inverse of mu, F of lambda mu, for alpha equal to the norm of mu. Okay. So well, mu is an element. Alpha was an element of the ground field, and mu is an element of this quadratic extension. Well, so maybe let me stop here for today. Well, our next goal will be, for example, to compute the characters of those representations, in fact of any representations. But this will happen only in March. And next time we will really classify the representations. Namely, I will prove that such representations are non-isomorphic to each other unless this eta tilde is equal to some eta tilde prime bar. Okay, so except for such involution, all the other representations will be distinct, pairwise non-isomorphic, and this way we'll see that we constructed everything. So I claim that now all the representations are really constructed. We only have to see which one are isomorphic, and once again, eta tilde and eta tilde bar will be isomorphic, and nothing else. That'll be that'll be on Friday, and then I plan to leave for 2 weeks, so the next time will be March 7. After this Friday, there will be a 2 weeks break. Okay. But please do come this Friday. And I will certainly send out a reminder not to come for the next 2 weeks. Thank you. Yes?
What's the reference you are using?
What is the reference I'm using? I think there was a book by Ilya Iosifovich Petetsky-Shapira. Something like representations. Of GL2 defined field. Something like this. But I can look it up. Maybe something is wrong. For example, maybe here it's not y, but I. Oops, sorry. Yeah, but it's impossible. Maybe something like this. And maybe also here it's I, not y. I'm not sure. And also, I'm not sure that it is in this book. I will look it up. Anyway, there is a book, the most famous book by Robert Langlands and Hervé Jacquet. Sorry. Automorphic forms on GL2. And well, certainly it's about the local fields and arrays, well, or global fields. But if you just consider a baby version of this, you will obtain what we study. So what we do is some baby version with many simplifications. Okay, so it's certainly contained here, but maybe also there. I forgot. I will look up. Okay. Thank you. And do I press some buttons now?